We've talked about the states of matter, and we've talked about the energy associated with the change in the state of matter. But now we need to look for those values that are not explicitly given. Typically, the values in tables or in problems are given as the delta H, or enthalpy of fusion, and vaporization. But sometimes we need to know the enthalpy of freezing or condensation. So let's look back at what we know about our phase changes. Notice that when we go from the left here, which is ice, over to vapor, what we see is that heat energy is taken from the environment, and this is actually an endothermic process. The reverse process, going from gas to liquid to solid, is an exothermic process, and heat energy is released to the environment. So exothermic means heat is leaving the system. Endothermic means heat is going into the system, and those are opposite processes. So let's illustrate this idea with a specific example. What is the enthalpy of condensation for CCl4 if the delta H of vaporization, or the enthalpy of vaporization, is 30 kilojoules per mole? Well, let's first think about the process that we're dealing with. We're dealing with liquids and gases. And as we go from a liquid to a gas, we're undergoing vaporization, which is an endothermic process. And then as we go from gas to liquid, we're dealing with condensation, which is an exothermic process. So the delta H of vaporization for CCl4, carbon tetrachloride, is equal to the negative of the enthalpy of condensation. Because these are opposite processes, the magnitude of the energy, meaning the numerical value, is the same, but the sign will be different. So what we find is that the enthalpy of condensation for carbon tetrachloride is minus 30 kilojoules per mole. Knowing that this is an exothermic process, it should come as no surprise that the value is negative. Let's see how we would use that information in a problem. So what is the change in energy when 25 grams of ice freezes? The enthalpy of fusion of water is equal to 6.01 kilojoules per mole. So the first thing we want to notice is that we have 25 grams of ice, but that our enthalpy of fusion in this case is given as kilojoules per mole. So we need to remember how we get from grams to moles. So we're going to use the molar mass of water, which is 18.02 grams per mole. We find that by using the information from the periodic table about the masses of each individual element. Now we need to look for the delta H of freezing. We're giving the delta H of fusion, and we know these are opposite processes. As a result, the delta H of freezing is going to be equal to negative 6.01 kilojoules per mole. Now we need to look at how we're going to set up the problem. We look for our simplest units first, which is in this case 25 grams. And what we see is 25 grams. And we're going to use our molar mass to convert from grams to moles. Remember, we're going to divide by the grams and multiply by moles. Then we can use our enthalpy of freezing, which we found is minus 6.01 kilojoules per mole. We see that grams cancel and moles cancel, and we can solve for our answer, which is going to be minus 8.34 kilojoules of energy.